Hi, this is Mrs. Barbara. This is AP Physics Chapter 13, Periodic Motion, Video 7. Today's topic is the physical pendulum. The objectives are: know the definition of a physical pendulum, understand for small angular displacement theta, the oscillations of physical pendulum are simple harmonic motion. Be able to calculate the properties of the motion of a physical pendulum. A physical pendulum is any real pendulum that uses an extended body in motion. Here you see the animation of a physical pendulum. What makes the physical pendulum oscillate? The oscillation of a physical pendulum is caused by a restoring torque, and that restoring torque is caused by the gravity, part of the gravity. Let's take a look at this irregular shaped body. It's rotating along the body is free to rotate around the z-axis. The gravitational force acts on the body at its center of mass, center of gravity. The restoring torque on the body is proportional to sine theta. So mg sine theta is the one that makes this object to rotate. However, when for small theta, sine theta is almost equals to theta, so the motion is approximately simple harmonic. So when the body is displaced as shown, the weight mg causes restoring torque. Remember, torque equals fd sine theta. So here is f mg, and here's d and sine theta. This negative sign shows the restoring torque and the theta are always in the opposite direction. When theta is positive going to the right, torque is going to the left. So when theta is small, we can approximate that torque z is negative mgd times the theta. So this is the equation for simple harmonic motion. One way to figure out what is omega is using this. Torque equals I alpha, so we can set this two equals to each other. We can determine alpha equals negative mgd divided by I times theta. So whatever in front of theta, this is omega squared. So we know omega equals to square root of mgd divided by I. And t equals 2 pi divided by omega, that equals 2 pi times square root of I divided by mgd. Another way to find it, we learned like the watch for the torque. So torque equals negative kappa times theta. This is simple harmonic motion in rotation form. In this equation, we know omega equals kappa divided by g. Kappa divided by I. Since kappa equals mgd, so omega equals to mgd divided by I. So from here, we can do the same thing. T equals to 2 pi omega, so we have the same expression. This is very important expression because from here, this equation is the basis of a common method for experimentally determining the moment of inertia of a body with a complicated shape. So first, we need to find the center of gravity of the body by balancing. Okay, you can put the object on the fulcrum where it balances. That is the center of gravity. Then we can suspend this irregular shaped body so that it is free to oscillate about an axis. That's the pivot. Then we can measure the period of the small amplitude oscillation. Then a small amplitude means theta is small. Finally, we can use this equation since we can measure the mass. We have determined d. We can measure t. That's how we can calculate I from that equation. Let's take a look at this example. A uniform rod of length L pivoted at one end, vibrate through a small angle, find the period of its motion. So a rod is a physical pendulum. So its torque equals mg. D is L over 2 from the center of the mass to the pivot. That's half of the length times sine theta. So for small angle oscillation, theta equals to sine theta, so torque equals negative mg L over 2 times theta. So in this case, kappa equals mg L over 2, and I, because this is uniform rod, so rotating at one end, so I equals 1/3 ml squared. So we can find omega equals kappa over I. That equals to mgl over 2, that's kappa. I is 1/3 ml squared. Simplify this expression, we have square root of 3g divided by 2l. Similarly, we can determine t equals to 2 pi divided by omega, so it's 2 pi times square root of 2l over 3g. That is a period. For a simple pendulum, 2 pi equals L over G. So this T for a uniform rod with the same mass and same length as a simple pendulum will have a shorter period because 2 over 3 is less than 1. Let's take a look at this example. You are given a non-uniform thin rod of mass m and length L with a pivot attached to one end. The center of the mass is located a known distance d from the end of the pivot. How do you determine the moment of inertia I rod of the pivot from the pivot with minimum error? So first, let's draw a free body diagram. I mean the diagram of the situation. So here is the irregular shaped rod, and here the top dot is a pivot. Over here, this is dot is the center of gravity that is given to you. They give us the distance between the center of gravity and d, and we have to determine I. Remember, I mentioned before, we can determine t in order to determine I from that equation. So let's derive that equation first. So from here, we have the torque equals mg times d times sine theta, right? That's negative mg d sine theta because, again, negative means the torque and the theta are always opposite in direction. If theta is small, sine theta is approximately equals to theta, so torque is directly proportional to theta. That means this motion is simple harmonic, and whatever in front of theta, that is your kappa. And here is the I, so from there we can find t equals to 2 pi I over kappa, so that becomes 2 pi I rod divided by mgd. So in order to find I rod, we just need to determine t. So how do we determine t? To determine t, so given m, d, and g, if we can determine t, we can determine I rod from that equation, right? To determine t, we simply lift a rod at a small angle. Has to be small, right? Otherwise, the motion is not simple harmonic. And let it oscillate. So how can we minimize the error? We can use a stopwatch to measure the time t of 10 oscillations in order to minimize the error. So instead of just measure time for one oscillation, so we do repeatedly 10 times. So how do we determine the period? Period equals to the time we measured divided by 10. That's the time for one cycle. Once we find t, we can put a t in this equation to find I. Okay, now suppose we were not given the location of center of the mass of the rod. How can we find the center of the mass? We can determine the center of the mass or center of gravity by placing the rod on a fulcrum. The center of the mass is the point above the pivot, above the fulcrum pivot. So when the rod balances, or we can push the rod at the edge of a table until it's just to tip over. Right? The point above the edge of the table is the point of center of mass. That's it. Let's take a look at another one. Oh, test your understanding. So the center of gravity of a simple pendulum of mass m and l and length l is located at a position of the pendulum bob, distance l from the pivot point. The center of gravity of a uniform rod of the same mass m and length 2l now pivoted at one end is also a distance l from the pivot point. So you have a pendulum and you have a rod, a long rod. So one is simple pendulum, one is physical pendulum. So the physical pendulum is longer, but their center of the mass have the same length. How does the period of this uniform rod compare to the period of simple pendulum? So again, let's take a look. For a simple pendulum, this is t equals 2 pi times square root of L over G. For a physical pendulum, we have t equals to 2 pi I over kappa, right? now I equals to 1/3 m times 2L squared, because that's the length of the what is it? Of the rod. So that gives us 4/3 ml squared. We know kappa equals mgl is the force times the distance, right? So we plug it in. T equals to 2 pi I over kappa. So we have T equals to 2 pi times square root of 4L over 3G. Compare this to T is bigger. T is bigger because its length, the rod's length is longer. So the rod has longer period. For the physical pendulum with length of 2L and mass m, its period is longer. That's it for today. Thanks for watching.